All right, hopefully the last part of the video, I'm trying to get these last three examples in all together. Just a little more practice here. So now I want to know what happens if I use a normal vector. And this is the same plane from the example that we did in part one. I just want to kind of show you a different method and a different way to play with these. And because we're dealing with the same points in the same plane, I've already given us the two vectors that I need. Well, the first thing I'm asking you to do, right, if I kind of just read through the problem and figure out how to attack this, is I need a normal vector. Well, how do I generate a normal vector? I know that the cross product of two vectors yields a normal vector, yields a vector that is perpendicular to the other two vectors that I have. So to save some time, I have already done that here. You can go back and verify my work if you want. If you want to pause it and work it out, that's fine. But for the sake of time, I'm going to keep on moving. One of the properties that we have from, or had from the vector equation of a line chapter or section is this property over here, this NP equals NA. This kind of relationship that, and there's a proof for it in the book that I'm not going to go through it, but this relationship that normal vectors are perpendicular to every other vector on the plane. So if I have two coplanar vectors, P and A, their dot products are the same, which is to say that they're 0. So I have my normal vector now, -4, -3, 1, or if you prefer, you can multiply that by -1 to reduce some of the negatives. I don't know why I just wrote addition there. P is the same P that it's always been, X, Y, Z. Same N from before. And A, again, pick a point, any point. I guess we'll stick with A just for the sake of clarity. My dot product, multiplying like components and adding them all together. So -4x plus -3y plus z equals, let's see, -4 minus 6 is -10 plus 1 is -9. You can see that my answer is the same but opposite in the sign, which is why, again, if you prefer just to deal with fewer negatives, you can just multiply it by -1. These are effectively the same here, just with the way that kind of planes operate. All right, well, let's work this out to 3 planes now. We know that the intersection of 2 planes is a line, but if I try to intersect a third plane with that, and this is really going to stretch my artistic ability or lack thereof. Let's see, here's 2 planes, right? And here's my line of intersection. And if I try to draw, let's see here, if I try to draw one more plane and maybe it goes this way. Yeah, this should work. If I go this way through my existing planes, here's the intersection of those 2 planes. You can kind of see that this right here, is the intersection of the 3 planes, one singular point. So now that we've gotten that art exercise out of the way, let's find this point of intersection, and it's just as easy as solving a system. So I'm going to show the setup, but I will leave you to solve this on your own. And what I probably will do is sidebar over to my calculator in a minute and just kind of refresh how to set this up. Right? It's just a system of equations. I want to find where these all meet, which means they all have to be equal. They have one point in common. So I trust you at this point to solve a system of equations by hand. We've been doing this for years now. But on the chance that this ends up on a paper too, you should be able to use your calculator and save yourself some time. So all we're going to do, there's a way to do this through matrices if for some reason the apps function doesn't cooperate on your exam. But assuming that it does, we're going to go to apps and we're going to look for this option right here, which looks like a lot of random letters, but it stands for polynomial and simultaneous equations. We have simultaneous equations, so we're going to go to option number 2. We have 3 equations. We have 3 equations with 3 unknowns. There we go. And if I click next, I just enter in my coefficients. So we've got 1, plus 2 minus 1 equals 4. We've got 2 minus 3 plus 1 equals -3. There we go. And 3 plus 1 minus 4. Whoops. Wait. Hold on. What if I just do it this way? Yeah, that works. Equals 1. Enter in all your items, press graph, and there's your solution right there. That point of intersection is 1, 2, 1. All right, back to the tablet for one more problem. And actually, this is something that we saw in chapter 3, way back in year 1, but I'm going to do this with just some different wording. So I want to determine the values of m such that the planes intersect. Well, this is just a fancy way of saying if they intersect, then the system has a solution. That's all it is. Again, this is just doing the same math as before, just with some new names. So let's business as usual. Let's set up my system. That was a terrible brace. There we go. X plus 5y plus 2z equals 6. 4x plus, and just for the sake of clarity, let's throw that in a different color, just so we can kind of keep my eyes on what I want to focus on. We're going to operate as normal and solve the system. I find it easiest, I think, to eliminate z here. So again, just by numbering these so I know which ones I'm dealing with, or so you guys know which ones I'm dealing with. Let's see. If I multiply twice the first equation and then add that to the second equation, I can eliminate z there. So 4x minus 6y minus 2z equals 10. And then x plus 5y plus 2z equals 12. So you get 5x minus y equals, well, this should be negative 10, so equals 2. No, it's not. It's positive 10. I'm getting lost in my negatives. Equals 22. And then if I apply the same process, let's see, it looks like I need to double equation 2 and add it to equation 3. So let's see, that's going to give me 4x plus 10y plus 4z equals 12, and 4x plus my minus 4z equals -1, and that's going to give me 8x plus 10 plus my equals 11. Okay, so here are our two equations now. And again, just to color code a little bit better, let's make that m stick out. Again, let's follow business as usual. Let's try to solve this for y. So I need to eliminate x, and this is where things might get a tiny bit messy. So if I multiply this one by 8 and multiply this one by -5, let's see, we're going to get 40x minus 8y equals 176, and -40x minus 5 times 10 plus my equals -55. We get some stuff. So the 40s cancel out. Let's see, I'm going to get, looks like, I'm just trying to figure out the best way to express this. I'm going to get -8 minus 5 times 10 plus my equals 121. Well, fortunately, the 121 is not relevant. In fact, the only thing that's relevant here is this coefficient on y. Because if I were to go solve this, this ends up in the denominator. And ultimately, I just want to make sure that this is not 0, right? Because if I'm solving for y, I don't want to divide by 0. So -8 minus 5, 10 plus m cannot equal 0. So let's see, doing some work here. If you prefer, we can distribute the -5 instead of fighting with the fractions. It's going to be 58, which I guess I'll just move over there now. So m cannot be 58 over 5, but can take on any other value to make sure that these planes intersect. So again, this is a problem that we saw earlier in Chapter 3. If you go find my videos from year 1, you will probably find a problem just like this, just maybe not worded the same way. And that's kind of my point here, is that these are the same problems that we've been seeing over and over and over and over. I'm just wording them in a different way.